Welcome back everyone. I thought we'd take a little bit of a break from our circuit calculations and show you where we would actually use some of these series resistive circuits that we've been talking about. So we started off with a single resistor, then we went to 2 resistors and then 3. So I'll give you an example of where we would use each one of those. So for the first one, it's a simple torch circuit. So where you get a torch, you put some batteries in the torch, you screw it on, then you flick the switch and light actually comes out. So this very first one we can have a look at with a single resistor can be likened to a torch. So you've got here a 4.5 volt power supply and a 20 ohm resistor. When we connect this up, what kind of current are we going to get? Well, 4.5 volts divided by 20 ohms, 225 milliamps. Okay, that's all good. So this circuit is just representative of this circuit that I've got down here. So if you have a look, I've got 3 1.5 volt batteries, so 1.5 plus 1.5 plus 1.5. That's where we get the 4.5 from. Very similar to what you'd have in a torch with 3 AA batteries. I've then got it connected to a light bulb. So this light bulb over here, when you connect it up to the batteries, you're going to get current flowing out of the negative up here through the filament inside the light bulb, out of the positive connection and over here to the positive terminal of the batteries. Now those electrons traveling through that wire inside the light bulb, that's going to cause friction. That friction gives you heat, and that heat actually generates light, so that's how the light bulb lights up. The more current we put through there, the more friction we have, because the more movement of electrons going through, and therefore the hotter it gets, so the brighter it gets. However, you don't want to blow it, so you need to be careful with that. So we can see with this particular circuit there's 225 milliamps of current flowing, and the light bulb is going to be pretty bright. So if we then want to limit the amount of current going through that light bulb, we can add a second resistor, and that's where we come to the 2 resistor circuit. So you can see here I've basically copy and pasted most of that circuit from the previous page. There's our 3 batteries to give us 4.5 volts. There's the light bulb, which is still a 20 ohm light bulb. But I don't want 225 milliamps of current flowing. I want to dim this light bulb a little bit. So what I've done here is I've included an extra resistor in series. So if you recall that if we put a couple of resistors in series, the 2 resistances add together to help limit that current even more. So we can slow down the current flow here. Now let's say I wanted to limit the current to 200 milliamps. So remember, we did have 225 milliamps flowing. Now we just want to bring that down by 25 milliamps, so we just want 200. What does this resistor need to be? Well, in order to figure out resistance, we need to know 2 things. Voltage, 4.5 volts, divided by current. The current that we want is 200 milliamps. So the current we want flowing in this circuit, total, is 200 milliamps. The voltage total is 4.5 volts, therefore in order to figure out the resistance total, we need to use those 2 values. Let's put it into the calculator. 4.5 volts divided by 200 milli, so exponential negative 3 to get milli, 22.5 ohms. So it is again, if you missed it, 22.5. So RT needs to be 22.5 ohms. If I redraw the circuit over here, there's my light bulb, 20 ohms. There's another resistor there, and we want the total of them to equal 22.5. Hopefully you can see that if we've already got 20 and we're trying to get 22.5, this guy needs to be 2.5 ohms. So I'm going to make this a 2.5 ohm resistor. 20, which is the light bulb, plus the extra little resistor in series, which is 2.5, gives us 22.5. If you then did 4.5 volts divided by this total resistance, you would get 200 milliamps. So we've slowed down the current in the circuit. The light bulb's a little dimmer because the current isn't flowing as fast. However, the battery will last longer. So that is an example of a 2 resistor circuit. Now the last one is a little more difficult. Well, you could probably see already. Lots of colors, looks very pretty. There's a component in here that we haven't spoken about yet. In fact, we won't speak about it until many lectures time when we get to operational amplifiers. However, all you need to know at the moment is these triangles, of which I've got 3, They've got two inputs and a single output each. What we're doing is with these comparators is it's comparing the two inputs. So it's comparing that black input to that red one, that black one to that yellow one, and that black one to that green one. If the black one is greater than the green or the yellow or the red, it will turn this light bulb on. That's all it's doing. If the black one is greater than whatever other voltage is coming in, it allows the light bulbs to turn on. Now, let's go to the circuit we have seen before. So this 3 resistor series circuit. So I'll draw it up here just so we can see it in more clarity. There's 3 resistors and I've got a 12 volt power supply. This resistor up here is 500 ohms, this one is 500, and the last one is 11K, so it's a lot bigger than the others. Now if you wanted to, you could do the calculations with this, but you would find, after finding out total resistance and total current and so forth, this guy has 0.5 volts dropped across him. This one, oops, is also 0.5, and this one is 11 volts. Or you could call 0.5 volts 500 millivolts, plus 500 millivolts, plus 11 volts, in fact I haven't got the V there, gives you 12 volts. Alright, so 11 there, plus 0.5 there, plus 0.5 there gives you the full 12. But then what we're doing here is, we've got this car battery over there, and the car battery should be 12 volts. But this little circuit that we've built is going to tell us how charged this battery actually is. So we first come along, we connect the battery up to our circuit, negative over to our negative here, so we've got a common negative connection. Then the positive goes into each one of these so we can compare what the positive terminal of the battery is compared to this point here. So let's just pretend that the battery here was, well, let's say it was 12 volts. So it equals exactly 12 volts. So we come along, there's 12 volts there, and there's 12 volts there, and there's 12 volts there. Now let's have a look at what's on the other 3 connections. On this connection, we're getting the voltage from this resistor by itself, which is 11 volts. So there's 11 volts coming in there. Oh, just trying to draw this a bit better here. Oh dear. Okay, 11 volts there. Have a look at the yellow one. The yellow voltage is actually getting R2 plus R3. So 11 plus 500 millivolts, or plus 0.5 volts, is 11.5 volts. So that's what's coming in on the yellow connection. If we look at the green connection, we're getting 500 millivolts plus 500 millivolts plus 11. So we're getting the full 12 volts coming in here. So if you recall, I just said that a comparator, this triangle, compares the two inputs. If the black input is bigger than what's on the colored input, the light turns on. So let's see which lights will turn on in this case. 12 volts coming in here. Is 12 volts greater than 11? Yes, it is. So this turns on. 12 volts coming in here. Is 12 volts at least, sorry, I say greater than, but at the moment let's just go with at least as big as. So is 12 volts at least as big as 11.5? Well, yes it is. So this one turns on. And then finally, is 12 volts coming in, so 12 volts from here coming in there, is that at least as big as 12 volts? Well, yes it is, so this one turns on as well. So this circuit is a battery level indicator. So we connect our battery to this circuit, and if all 3 lights light up, then it means yes, this battery is good. But what if, let's just get rid of these, what if this voltage here was, let's go with 11, let's get a pen, let's go with 11.3 volts. So we get our car battery, we connect it up to our special circuit, battery level indicator circuit, and we're going to do the same thing. So this voltage equals 11.3. Is 11.3 greater than 11? Yes it is. So this one turns on. Is 11.3 greater than 11.5? No, it is not. So that does not turn on. And is 11.3 greater than, at least as great as 12? It is not. So that one does not turn on. So in this case, when the battery is a bit low, at 11.3 in this case, only the red lights up. So we connect it up to our battery charger, and as it charges up, let's say it comes up and it gets to 11.7. So 11.7 is greater than 11, so that one's still on. 11.7 is now greater than 11.5, so this turns on. However, it's not greater than this one, so the green's not on yet. So you can see it's just showing us the charge level that we've got in our battery. And we did that all from using 3 resistors, and we chose specific values of resistors so that we got 11 volts across this one, and then that 11 volts went into the first comparator. We then made sure that there was 0.5 across here, and the voltage we fed into the comparator, because see how the negative is connected down here, it means the voltage coming in here, here, and here is reference to that point. So between this point and that point is 11. Between this point and that point is 11 plus 0.5, so it's 11.5. And the voltage between this point and this point is now 12, which is 0.5 plus 0.5 plus 11. Hopefully that kind of sunk in then. But everything that you see here we're going to cover in more detail, and you will completely understand, or it's my intention that you'll completely understand how these comparators actually work when we actually get to a lecture about them. Alright, continue on, because there's no homework for this one, there's no quiz for this one, however there will be for the very next lecture. So thanks for watching again, guys.